Hi everyone and welcome to my presentation. I'm Andres and today I am talking about a work we recently published that describes the motion of entangled polymers subjected to an active motion. First things first, let's start by introducing the physical framework. On the one hand, our theory relies on the physics of linear entangled polymers. And the model that best describes the physical behavior of such systems is the reptation or tube theory. This is a concept originally introduced by de Gennes and later developed more detailed by Doi and Edwards. This model has been useful in describing the physics of polymer melts, gels, or rubbers. On the other hand, we also exploit the physics of active matter. This is a relatively young field that describes the motion of cell-propelled particles that uses energy either internal or from the environment. Typical examples of these kind of systems are bird flocks, school of fish, bacteria, some genus particles, as well as some molecular motors such as kinesin or myosin. So, in summary, we use both fields to develop our model. We employ the reptation model of entangled polymers, but we also introduce to this model an active motion that we named as drift. To this day, we have these two publications about this topic. Now, let me remind you some of the basic hypotheses of the reptation model. As I said before, the tube rotation theory attempts to capture the dynamics of polymers moving through a mess of obstacles, using a virtual tube as a mean field potential. And thus, the dynamics of the polymers, of these entangled polymers, can be simplified to a diffusive motion in one dimension. The basic parameters of the model are the one-dimensional diffusion coefficient, the size of the entanglements, or the size of the tube, the number of entanglements set, and the length of the tube. The reptation model predicts the following relations. The relaxation time, characteristic of the system, is proportional to the cube of the molecular weight. The viscosity, which is proportional to the relaxation time, is again proportional to the cube of the molecular weight. And finally, the diffusion coefficient of the center of mass decays with the square of the molecular weight. In our work, we implement an additional relaxation mechanism, a drift that acts along the contour of the tube, pointing in one of its directions. This kind of motion can be produced using a mass that has some molecular motors attached, and the proof polymer swimming through this mesh. This polymer can be catch by these molecular motors that pull the polymer in a certain direction due to some affinity. Before showing some results, we must establish some conditions since we want to preserve the advantageous simplicity of the tube model. This is the one-dimensional description. To do so, the value of the drift must be restricted, taking into account the entanglement size, the distance between entanglements, and the typical relaxation time of one entanglement. So the ends of the tube of the polymer can explore all possible orientations before being entangled again. Using this basic hypothesis and the mathematical tools of the rotation theory, we've been able to solve analytically the tube segment survival function and the tube survival function, both related with viscosity. We have also solved the segmental motion of this system that is related with the diffusion coefficient of the center of mass, or with the diffusion of the system. And finally, we have computed the dynamic structure factor that is very important in experiments of scattering. By doing some scaling arguments, we can predict some of the results when the drift is significant. So in this regime, we must have this condition, okay, that the relaxation time due to the drift, that is given by this relation, is much smaller than the relaxation time in the pure reptation model, okay? So this gives us this linear dependence on the molecular weight, and this condition for the drift to be significant. Consequently, the viscosity that depends on the relaxation time will also depend linearly on the molecular weight. And finally, the diffusion coefficient of the center of mass becomes a constant when the drift is the main relaxation mechanism, so it does not depend on the molecular weight. In other words, this first relation implies that no matter how small the value of the drift is, that you can always find a polymer with a sufficiently large molecular weight for the drift to be the main relaxation mechanism. And the second and third relation show that the transport properties are dramatically enhanced in contrast with the pure rotation theory. So now let's move on to the analytical results. So let's start by examining the tube segment survival function. As the chain rotates inside the tube, the segments of the original tube are destroyed every time one of the chain ends reaches these segments. In other words, this observable measures the probability that an original tube segment remains after some time. If we plot this function for a tiny value of the drift, or in the case of pure rotation, we see that the tube is dilated equally in both sides of the tube as time evolves. This would be curves for short times, this would be this time, okay, and this for later times. As we increase the value of the drift, the function becomes more and more asymmetric in the direction of the drift. As you can see, in this case, the function is even more asymmetric, and for very significant values of the drift, this function becomes completely asymmetrical in the direction of the drift. And for same times, it decays much faster than in the pure rotation regime. If we inspect the tangent-tangent correlation function, we see a similar behavior. This observable measures the correlation between the orientation of different parts of the polymer. Okay? So, in the case of pure rotation, or for a very tiny value of the drift, at short times, only the closest parts of the polymer are correlated, and as this system evolves, this correlation diffuses equally in both directions of the tube. Alright. However, when the drift is the main relaxation mechanism, when the drift governs the dynamics, we can see that this correlation is pulled in the opposite direction of the drift. And this is reasonable since these are the last parts, these are the last parts that leave the original tube. We can change the point of view of the argument by setting the value of the drift and increasing the number of entanglements. Okay. As I stated before, the viscosity has a power law of 3 in the case of pure rotation, whereas when the drift governs, it becomes linear with the molecular weight. Similarly, in the case of the diffusion of the center of mass, in the case of the pure reptation, we had a power law of -2, whereas it becomes a constant when the drift is the main relaxation mechanism. In order to support our analytical results, we carried out Brownian dynamic simulations. The evolution equation is given by the discrete version of the Langevin equation, where we have this harmonic force between the beats, the diffusion term, but we also have this drift term due to our model. Basically, this Rheau's model inside the tube adds a relaxation mechanism that destroys the ends of the tube much faster at short times. The system evolves in one dimension, okay, but then is projected in the three-dimensional real space. This has allowed us to study the survival functions and the segmental motion of the entangled polymers with drift. I want to remark that these contour length fluctuations affect the dynamics at short times, so the behavior described analytically is approximately recovered using an effective number of entanglements. Thus, all the arguments exhibited before can be applied here, but using this effective number of entanglements. For instance, this similarity can be seen in these figures, where we plot the tube segment survival function. The decays is similar at same times, but these extremes of the tube are destroyed much faster. This is the case with a very tiny drift, and this is the case with a very significant drift. Okay. As an example of the results we obtained, here I show you the mean square displacement of the central bead and the mean square displacement of the center of mass. In the last panel, we have divided the observable by the square root of the time to show this regime. Okay? And as you can see, if the drift is the main relaxation mechanism, if the drift governs the dynamics, the final diffusive regime can be reached even before the Rheau's time. In the case of the center of mass, we see a superdiffusive regime, since we have divided the observable by time. Okay? So we have this terminal diffusive regime, but to reach this part, the center of mass passes through a superdiffusive regime when the drift is the main relaxation mechanism. Here we can summarize the results of the mean square displacement of the central bead and the mean square displacement of the center of mass. In G1, we see how the last Fickian regime, this diffusive regime, can be reached even before tau Rheau's, with the only condition that the drift governs and tau c must be smaller than tau Rheau's. Okay? In the case of G3, of the mean square displacement of the center of mass, we see this superdiffusive regime before the final Fickian regime for significant values of the drift. I'd like to conclude this presentation summarizing some important ideas. In this work, we have developed a theoretical model based in the rotation RTO theory, but introducing this active motion, this drift. We solved analytically the dynamics of this model, and the predictions we obtained have a very good agreement with the Brownian dynamic simulations we performed. This model might be useful in the context of biophysics, describing the motion of some molecular motors, and also in drug delivery, for instance. Finally, I'd like to remark that in the following months we'll carry out molecular dynamic simulations to support our theory and its predictions. So we will explore how this drift can be measured experimentally. Thank you for your attention and see you soon.